The knowledge of quantum mechanics, together with Einstein's theories of relativity, really gave us the modern world.
By the end of the 19th century, it was already known that we needed some new physics to explain mysterious phenomena. Albert Einstein, the genius who revolutionized our understanding of the universe, once said that God does not play dice. For decades, this belief shaped modern physics. Relativity is the foundation of modern physics, along with quantum theory. But what if he was wrong? In a groundbreaking discovery, quantum computers have revealed something that would have shaken Einstein's worldview to its core. We got news from Geneva, Switzerland, that Einstein might be wrong. What is this new evidence? Let's find out. In a groundbreaking revelation, quantum computers have unearthed evidence that challenges one of the most celebrated minds in history, Albert Einstein. This discovery shakes the foundation of Einstein's belief in an orderly, deterministic universe. But to understand how we arrived here, we must first explore the early years of this revolutionary thinker and the profound ideas that reshaped our understanding of reality. The year was 1905, and a young Einstein, employed as a patent clerk in Bern, Switzerland, was on the verge of scientific immortality. That year, later dubbed his Annus Mirabilis *, Latin for miraculous year, Einstein published 4 papers in the prestigious *Annalen der Physik * journal. Each of these papers contributed a groundbreaking idea to modern physics and established him as a force to be reckoned with in the scientific world. The first of these papers addressed the photoelectric effect. At the time, light was largely understood as a continuous wave, a view supported by classical physics. However, Einstein proposed that light could also behave as discrete packets of energy, later called quanta. This counterintuitive idea laid the foundation for quantum mechanics, the field of study that would eventually challenge his own beliefs. In his second paper, Einstein explained the phenomenon of Brownian motion, the random movement of particles suspended in a fluid, by applying statistical mechanics. He offered empirical proof for the existence of atoms and molecules, solidifying the atomic theory of matter. This work not only advanced the understanding of microscopic processes but also validated the concept that matter is made up of indivisible particles. Einstein's third paper, however, was his most revolutionary. In it, he introduced the special theory of relativity, a bold reimagining of space and time. Classical mechanics, derived from Isaac Newton's work, treated space and time as absolute and unchanging. Einstein argued instead that they were interwoven into a single fabric, space-time, and that the measurements of space and time were relative, depending on the observer's motion. The most striking implication of this theory was the constancy of the speed of light, which remains the same for all observers, no matter their relative speed. The final paper of Einstein's miraculous year built on his theory of relativity and delivered the now famous equation *E equals mc²**. This deceptively simple formula revealed that mass and energy are interchangeable, a principle that would have far-reaching consequences, including the development of nuclear energy. Together, these 4 papers catapulted Einstein from the obscurity of a patent office to the forefront of theoretical physics. At the heart of Einstein's early work was a vision of the universe as an orderly, predictable system, a grand cosmic clockwork. This view was inspired by the deterministic principles of Isaac Newton. In Newton's universe, every motion, from the fall of an apple to the orbit of planets, could be described and predicted by mathematical laws. For over 2 centuries, this framework had been the cornerstone of physics, offering a sense of stability and certainty about the natural world. Yet, even as Albert Einstein advanced this legacy, cracks were forming in the Newtonian paradigm. Experiments at the atomic and subatomic levels began to reveal phenomena that classical physics could not explain. Light, for example, showed dual properties, behaving as both a wave and a particle. Electrons defied intuition by appearing to exist in multiple places at once or by disappearing and reappearing without predictable patterns. Such findings hinted at a universe that was far less deterministic than Newton and Einstein had envisioned. Ironically, It was Einstein's own work on the photoelectric effect that helped ignite the field of quantum mechanics, the branch of physics dedicated to understanding the strange and unpredictable behaviors of particles on the smallest scales. While his equations revealed the quantum nature of light, he was deeply unsettled by the implications of this new physics. The quantum world appeared to be governed not by strict causality but by probabilities, which was a direct challenge to his belief in a universe ruled by order. By the 1920s, quantum mechanics was gaining traction among physicists. Experiments consistently confirmed its predictions, and theoretical developments began to describe the bizarre behaviors of particles with unprecedented precision. However, these advances only deepened the divide between the emerging quantum view and the classical view Einstein championed. The orderly, deterministic clockwork of Newton and Einstein was being overshadowed by the probabilistic, and at times seemingly chaotic, nature of the quantum realm. Einstein's discomfort with quantum theory would soon lead to fierce debates with other prominent physicists, including Niels Bohr. But in 1905, as he unveiled his groundbreaking ideas, Einstein was a young scientist pushing the boundaries of knowledge, unaware that the very revolution he was helping to spark would later challenge his deepest convictions. The conflict between classical physics and quantum mechanics was not just a scientific debate, it was a philosophical struggle over the nature of reality itself. For Newton and later Einstein, the universe was a grand mechanism, each cog and wheel moving in harmony according to unchanging laws. Predictability and determinism were its defining features. In contrast, quantum mechanics suggested a world where uncertainty reigned, where particles behaved unpredictably and could influence each other instantaneously across vast distances. This growing tension between order and chaos, between determinism and probability, set the stage for one of the greatest intellectual battles in the history of science. As the 1920s unfolded, the landscape of physics was undergoing a major transformation. Quantum mechanics, a new and enigmatic framework, was emerging to describe the behavior of particles at the atomic and subatomic levels. This nascent theory introduced concepts that defied classical intuition, challenging the deterministic worldview that had dominated physics since Isaac Newton. Albert Einstein, whose earlier work had already revolutionized our understanding of space and time, found himself increasingly at odds with these developments. Einstein's discomfort with quantum mechanics stemmed from its inherent probabilistic nature. Unlike classical mechanics, which could predict the future state of a system with precision given its initial conditions, quantum mechanics dealt in probabilities. It suggested that certain pairs of physical properties, like position and momentum, could not both be known to arbitrary precision simultaneously, a principle known as the Heisenberg uncertainty principle. This indeterminacy was unsettling to Einstein, who famously remarked that God does not play dice with the universe. Central to his objections was the phenomenon of quantum entanglement. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper that would become one of the most famous critiques of quantum mechanics, known as the EPR paper. It presented a thought experiment designed to illustrate what they saw as the incompleteness of quantum theory. They considered a pair of particles that had interacted and then separated. According to quantum mechanics, the properties of these particles were not independent but entangled, meaning the state of one particle was directly related to the state of the other, no matter how far apart they were. Einstein and his colleagues argued that if you could predict the position or momentum of one particle by measuring the other without disturbing it, then these properties must be elements of reality not accounted for in quantum mechanics. They concluded that the quantum mechanical description of physical reality was incomplete. This paradox challenged the Copenhagen interpretation of quantum mechanics, which held that particles do not have definite properties until they are measured. Niels Bohr, a leading proponent of the Copenhagen interpretation, responded to the EPR paper by emphasizing the principle of complementarity. He argued that the properties of particles are not predetermined but are brought into existence through the act of measurement. Bohr contended that the EPR thought experiment did not reveal any incompleteness in quantum mechanics, but rather highlighted the necessity of considering the experimental context when discussing physical phenomena. The debates between Einstein and Bohr were not merely academic. They touched upon the fundamental nature of reality. Einstein believed in an objective reality that existed independently of observation, a viewpoint known as realism. He also held to the principle of locality, which posits that objects are only directly influenced by their immediate surroundings. Quantum mechanics, with its entangled states and non-local correlations, seemed to violate these principles. Einstein's discomfort with quantum mechanics was not limited to philosophical objections. He was concerned that the theory's probabilistic nature undermined the predictability and determinism that he believed were essential to a complete physical theory. He sought a more complete theory that would restore determinism and locality, often referred to as a hidden variable theory. Such a theory would account for the apparent randomness of quantum mechanics by positing underlying variables that determine the outcomes of measurements. Despite his reservations, Einstein's critique spurred further investigation into the foundations of quantum mechanics. In the decades that followed, experiments were designed to test the predictions of quantum mechanics against those of hidden variable theories. These experiments, particularly those involving Bell's theorem, have consistently supported the non-local predictions of quantum mechanics, suggesting that the universe is indeed more interconnected and less deterministic than Einstein had envisioned. But could it be that modern quantum computers have proven his most groundbreaking work wrong? We will find that out really soon. After reshaping our understanding of the universe with his groundbreaking theories of relativity, Albert Einstein turned his attention to an even greater challenge: uniting all fundamental forces of nature into a single cohesive framework. His ambitious pursuit of a unified field theory consumed much of his later life, driven by his belief in the harmony and simplicity underlying the universe. While this quest would remain incomplete at his death, it laid the groundwork for some of the most profound questions in modern physics. Einstein's journey toward unification began with the general theory of relativity, published in 1915. This elegant theory depicted gravity not as a force acting at a distance, as Newton had described, but as the warping of space-time by massive objects. While revolutionary, it only addressed gravity and left out the other known force at the time, electromagnetism. Einstein believed there must be a deeper connection between these forces and sought a single theory to reveal the symphony of nature's laws. His search for unification led him to explore various mathematical approaches. One such attempt was his work on teleparallelism in the late 1920s. This framework reimagined spacetime as having a geometric structure that allowed for parallel transport of objects. Einstein hoped this alternative geometry might reveal links between gravity and electromagnetism. Despite its elegance, the approach fell short of unification, and Einstein moved on to other ideas. The greatest challenge Einstein faced was the rise of quantum mechanics, which was rapidly reshaping physics during this period, revealing a universe of uncertainty and probability that clashed with Einstein's vision of a deterministic world. As I have already explained, central to his rejection of quantum mechanics was its departure from locality, the idea that objects are only influenced by their immediate surroundings. In contrast, quantum mechanics suggested that particles could become entangled, meaning their properties were intrinsically linked regardless of distance. Measuring one particle's state instantly determined the state of the other, even if they were light years apart, a phenomenon Einstein derisively called spooky action at a distance. In 1935, along with Boris Podolsky and Nathan Rosen, he published the EPR paper, arguing that quantum mechanics was incomplete. The paper described a thought experiment involving entangled particles, showing how quantum theory appeared to violate locality and determinism. The authors concluded that quantum mechanics must be missing hidden variables that would restore a deterministic framework. However, Einstein's critique did not halt the progress of quantum mechanics. Physicists like Niels Bohr and Werner Heisenberg championed the Copenhagen interpretation, which embraced the probabilistic nature of quantum mechanics. Bohr argued that particles did not possess definite properties until they were measured, and the apparent paradoxes of entanglement reflected the limits of classical thinking. As the quantum revolution advanced, Einstein's efforts to unify gravity and electromagnetism became increasingly isolated from mainstream physics. Quantum field theory, QFT, which integrated quantum mechanics with special relativity, emerged as the dominant framework for understanding particle interactions. By the mid-20th century, QFT had achieved significant success, unifying electromagnetism and the weak nuclear force into the electroweak theory. It also described the strong nuclear force that holds atomic nuclei together. Despite these advances, gravity remained the outlier. QFT struggled to incorporate gravity, as its mathematical structure led to infinities that defied resolution. Einstein's later years were marked by a sense of isolation. While he remained a towering figure in the scientific community, His refusal to embrace quantum mechanics put him at odds with many of his peers. Undeterred, he continued refining his unification theories, confident that a deterministic explanation of the universe would emerge. He worked tirelessly, penning equations and exploring new frameworks, until his passing in 1955. Though Einstein did not achieve his goal, his quest for unification influenced subsequent generations of physicists. The pursuit of a theory of everything, a framework uniting all fundamental forces, including gravity, remains a central challenge in physics. String theory, for example, posits that all particles are tiny vibrating strings, with their interactions governed by a unified mathematical structure. Another approach, loop quantum gravity, attempts to reconcile gravity with quantum mechanics by quantizing space-time itself. Yet, they now all rely on quantum computing to solve some of the world's greatest mysteries. So, before we get to the new evidence this technological marvel has conducted, we should first talk a bit more about how it operates and how it became so popular in the first place. The origins of quantum computing can be traced back to the early 20th century with the development of quantum mechanics by pioneers such as Max Planck, Albert Einstein, and Niels Bohr. These foundational principles set the stage for later explorations into quantum computation. In 1980, physicist Paul Benioff introduced the concept of a quantum mechanical model of a Turing machine, laying the groundwork for quantum computing. Building upon this idea, Richard Feynman, in 1982, proposed that quantum systems could be simulated more efficiently using quantum computers than classical ones, stressing the potential advantages of computing with quantum systems. In 1985, David Deutsch formalized the idea of a universal quantum computer, proposing the first universal quantum Turing machine. This theoretical model extended the capabilities of classical computers by incorporating quantum principles, suggesting that certain computational problems could be solved more efficiently using quantum algorithms. The 1990s marked significant progress in translating quantum computing theories into experimental reality. In 1994, mathematician Peter Shea developed an algorithm capable of efficiently factoring large numbers, a task that is computationally intensive for classical computers. Shea's algorithm demonstrated that quantum computers could potentially break widely used encryption schemes, underscoring the practical implications of quantum computation. Following this, in 1996, Love Grover introduced an algorithm that provided a quadratic speedup for unstructured search problems, further showcasing the potential of quantum algorithms to outperform their classical counterparts in specific tasks. Experimental validation of these theories began in earnest in 1998, when a 2-qubit quantum computer was developed, demonstrating the feasibility of quantum information processing. This milestone paved the way for subsequent experiments that incrementally increased the number of qubits and improved coherence times. The early 21st century witnessed rapid advancements in quantum computing technologies. In 2011, the first commercially available quantum computer was released, marking a significant step toward the practical application of quantum technologies. In 2019, Google announced that its 54-qubit quantum processor, named Sycamore, had achieved quantum supremacy by performing a specific task more efficiently than the fastest classical supercomputers. Concurrently, companies like IBM and Microsoft have made significant investments in quantum computing, developing cloud-based platforms that provide researchers and developers with access to quantum processors. These initiatives have democratized access to quantum technologies, fostering a global community of practitioners exploring diverse applications. Quantum computing leveraged principles of quantum mechanics to process information in fundamentally new ways. Unlike classical bits, which represent either a 0 or a 1, quantum bits, qubits, can exist in multiple states simultaneously, a phenomenon known as superposition. This allows quantum computers to process a vast number of possibilities concurrently. Another critical principle is entanglement, where qubits become correlated in such a way that the state of one qubit directly influences the state of another, regardless of the distance separating them. Entanglement enables complex information processing capabilities that are unattainable with classical systems. Quantum computers also use interference, where the probability amplitudes of quantum states can reinforce or diminish each other. By carefully orchestrating interference patterns, quantum algorithms can be designed to amplify correct outcomes while suppressing incorrect ones, enhancing computational efficiency. Despite the promise of quantum computing, several significant challenges have impeded its development. qubits are highly susceptible to decoherence, where interactions with the external environment cause them to lose their quantum properties. Maintaining qubit coherence for sufficient durations to perform complex computations requires isolating them from all forms of environmental noise, often requiring operations at temperatures close to absolute zero. Error correction presents another formidable challenge. Quantum error correction schemes are essential to detect and rectify errors arising from decoherence and other quantum noise. However, implementing these schemes is resource-intensive, often requiring a large number of physical qubits to create a single logical qubit with protected quantum information. Scalability remains a critical hurdle. Building quantum processors with a large number of qubits while ensuring high-fidelity operations and inter-qubit connectivity is a complex engineering endeavor. Early breakthroughs have demonstrated the feasibility of small-scale quantum processors, but scaling these systems to practical, large-scale quantum computers continues to be a significant focus of research. The pursuit of more advanced quantum computers has become a global endeavor, with significant investments from governments, academic institutions, and private enterprises. In the United States, the National Quantum Initiative Act was enacted to accelerate quantum research and development, fostering collaboration across sectors to maintain leadership in this critical technology. Internationally, countries like China and members of the European Union have launched substantial quantum programs, recognizing the strategic importance of quantum technologies. And now, one of them has some great groundbreaking information to present. Reports indicate that none other than Google just discovered new evidence. Their quantum computers just proved Einstein wrong. In a groundbreaking experiment using their most advanced quantum computing system, researchers observed phenomena that directly challenged Einstein's fundamental beliefs about the nature of reality. Some even go as far as saying that it was all a lie. The experiment, which involved creating a complex quantum simulation of space-time itself, revealed that entangled particles don't just communicate instantaneously across distances. They actually influence the very fabric of reality. This discovery strikes at the heart of Einstein's deterministic worldview and his famous objection to quantum mechanics. What makes this finding particularly significant is how it builds upon Einstein's own work. While his theories of relativity brilliantly described how gravity warps space-time, this new quantum experiment suggests something even more profound. Space-time itself may emerge from quantum processes. In other words, the quantum realm that Einstein was so skeptical of might be more fundamental than the classical physics he championed. The implications are staggering. If space-time emerges from quantum processes, then Einstein's conception of reality as a smooth, continuous fabric needs to be reconsidered. Instead, at its most fundamental level, the universe appears to be composed of discrete quantum elements that interact in ways that defy classical physics. Perhaps most dramatically, the experiment demonstrated that quantum entanglement, the phenomenon Einstein famously dismissed as spooky action at a distance, isn't just a curious feature of particle physics. It appears to be a fundamental aspect of how the universe works at its deepest level. When particles become entangled, they don't just influence each other's properties. They create ripples in the very structure of space-time. This discovery doesn't invalidate Einstein's theories entirely. General relativity still brilliantly describes gravity and the large-scale structure of the universe.